I want to finish up our treatment of phase equilibria and phase transitions by introducing you to a simple version of the phase rule. Now, what is a phase rule? Well, it's basically something that tells us something about the features that we find on a phase diagram. So let me explain what I mean. I'm going to label a few things. I'm going to say C is equal to the number of components that we have represented in the phase diagram. In this case, that's the number of different substances. So if I had, I don't know, water and ethanol, then those would be two components. Now, so far what we've been talking about all have one component, so we're going to have C equals 1 for all of the things that we've talked about so far. When we get to the next module, we'll see instances where we have C more than 1, and that's when the phase rule is going to come in more handy. We also can define P as the number of phases that are present in a given feature. Okay, so phases being solid, liquid, gas. How many of them are there present on a given feature? And finally, F is going to represent the dimensionality of the feature. And again, all of these things will become a little clearer when I explain this a little bit further. Okay, so what do I mean by all this? Well, for example, let's look at this phase diagram that I've drawn over here. Now, I could take this phase diagram and basically take the solid area and say I'm just going to shade it in. So all of this is solid, every place where I've got a shade. And then I could similarly do something for the liquid part of the phase diagram and shade it in. So all of that is liquid. And then similarly, I could do the same for the vapor and shade it in. So all of these shaded regions would represent solid, liquid, and vapor. Now, what that means as far as this is concerned is that these shaded regions have a total of one phase. In other words, within this shaded region here, I have only liquid. I don't have any solid or vapor in that region. So for that shaded region, I have that the number of phases is 1. Now, what that means in practicality is that I can vary both pressure and temperature without changing the phase. So within this feature, I'll write this up here, I can vary both pressure and temperature within the feature without crossing a boundary or without going to an area that has more than one phase. All right, so that's one example of this. Now, since I can have both of these things change, I would say in this case that I would define F, the number of the dimensionality of the feature, is equal to 2. So in other words, it is an area, so it has dimensionality of 2. All right, what's another example that I can have here? Well, how about the coexistence curves? We've been spending a lot of time talking about those coexistence curves. All right, in each of these coexistence curves, so this is one of them, this is another one, and this is a third one. But on each of those coexistence curves, I have two phases represented. So on this red curve, I've got both liquid and vapor. On the purple curve down here, which now is looking blue, I have both solid and vapor. And on the blue curve up here, I have both liquid and solid. So I always have two phases on one of these curves. But the dimensionality of the curve itself is just equal to 1. It is a line or a curve, so it has a dimensionality of 1. Finally, and there aren't very many examples of this in this, but on the triple point, it is a single point. Okay, right here is the triple point. And the triple point has a total of 3 different phases associated with it. And since it has a dimensionality of 0, that means that the number of degrees of freedom, or dimensionality of that, is equal to 0. I should have mentioned on the coexistence curve, I can vary either P or T, but I can't vary them both, because if I vary one, the other one is going to be completely fixed by staying on that curve. In the case of the triple point, I can't vary any of those, because as soon as I vary one of those parameters, pressure or temperature, I'm going to move away from the triple point. I'm no longer going to be in a region that features three different phases. So when I look at all of this, what I would find is that, in fact, if I add the number of phases to the dimensionality, I will always have P plus F is equal to 3. Look, 1 plus 2 is 3, 2 plus 1 is 3, 0 plus 3. 0 plus 3 is 3. So this, in fact, is the relationship that I'll find between these things. And the way we would normally write this is that we would write the phase rule as F is equal to 3 minus the number of phases. So really all this phase rule is doing is telling us about what kind of feature to expect for some number of different phases. When we only have one component, this is pretty easy and pretty basic. In fact, I would even say pretty trivial. But when we have more than one component, that's when things get interesting, and we'll see some examples of that in the next module.